Hello everyone and welcome to our first lecture of operating systems course, which is Introduction to Operating Systems. This is the foundation of how computers operate, and understanding it will be important in your journey as future computer scientist. First of all, as this course is an asynchronous course, as you may already found your syllabus in Moodle, so in the syllabus you will see that's an asynchronous course, and you will find all the recorded lectures on every week's content. You will get the PowerPoint slides, lecture slides, and also the YouTube video link to view your recorded lectures. And other than that, if you have any question about the syllabus and on any lecture, you will have a discussion forum on every week's content, and you can always email me, and we can have the Zoom meeting whenever you will need help. Or my office hours are 10 to 12 on Fridays, so you can also email me if you want any help on that time. So basically, as we are starting our course, I just wanted to make you comfortable that I am here for you whenever you need. So don't hesitate, and always email me for any kind of question or any problem or any concerns. So let's get started. So in today's session, we'll explore what operating systems are and their functions and their role in managing computer hardware and softwares and these general steps. So basically, we'll start with a simple definition. An operating system, or OS, is a type of software that acts as an intermediary between the user and the computer hardware. It ensures the efficient management of system resources. So, if you think of the operating system as a traffic controller that organizes all the hardware and software in your computer to work harmoniously. So here we can say, why are operating systems essential? Like operating systems play a crucial role in enabling user-friendly interaction with computers. Imagine how difficult it would be to use a computer without a graphical interface or commands to manage files and programs. Like if you think like whenever you're using a Windows computer or Mac computer or Linux, if you think like how difficult it would be if there is no Windows or no graphical user interface for us, like people who is not from programming background, or general people who is not familiar with the computer system or computer function, then it will be very hard for them to use a computer. Like using a operating system, by using an operating system, it is so easy that you can see whatever you're doing. You can just click you can create a new folder, you can copy a file from one file to another file, you can change file like the information in the file, you can do whatever you want to do. So this is very important for a computer, and it's a very important user friendly interaction with computer for users. Like users need operating system to communicate with computer. We can just simply say that. Now the operating system ensures optimal utilization of resources, balancing the needs of applications and users. So if we see like a overview of operating system evolution, um, if we just say like operating systems have come a long way, because like from simple batch processing system that executed one program at a time to today's sophisticated multitasking and real-time systems, it has come so far. Like key advancements we can say include time sharing systems in the 90s 60s, personal computing in the 1980s, and modern mobile operating systems like iOS and Android. So these are the highlights, milestones that it has come across a very long way. So these are the basic functions of an operating system. So first is process management. We will go through all these functions step by step in detail, but now I'm just going through this just simply so first of all, the process management. So it is one of the core functions of an operating system. It involves creating, scheduling, and terminating processes. For instance, when you open multiple applications such as a browser and a word processor, the operating system ensures that each process gets enough CPU time without interfering with each other. So that's how process management works. Then memory management. So memory management ensures the efficient allocation of memory to processes. It handles which processes get memory and manages swapping between RAM and storage when necessary. Then we have file system management. The file system organizes and manages data storage. It keeps track of where files are located and provides access control. Then we have device management. Well, the OS acts as a bridge between the computer and its devices, like printers, keyboards, and monitors. So that's how we can manage devices. Like we have device drivers in our OS. So we will go through all these functions in detail in our future lectures. Okay, next is security and protection. Well, the OS protects the system from unauthorized access and ensures the integrity of data. Then networking. The OS enables networking by providing protocols and managing data transfer between computers. Okay, so now first we'll start with process management. Well, what is process? So basically a process is an active instance of a program in execution, including its code, data, and current state. While a program is passive, a process is a dynamic entity. For example, when you open your browser, the browser's program becomes a process with allocated memory, CPU resources, and a state. Okay, process state. So we'll see the life cycle of the process state here. Now, processes go through various states during their life cycle. This includes new, ready, running, waiting, or terminated. Now, when it is on the new state, it means the process is being created. So it's a new process. Then if it's waiting to be assigned to the CPU, it is ready. It's on ready state. Then if it's currently executing on the CPU, it is on running state, that it is running, it's executing. Then if it's waiting for a resource or IO operation to complete, IO means input output operation to complete, that means it's on waiting state. Last is the process has finished execution, it means it's terminated. So this is how the process state has the life cycle, and it just go through these various states. For example, if we say imagine a person ordering food in a restaurant, the states are like ordering, waiting for preparation, eating, and leaving. So these are the states if we think about real world analogy. Okay, next is process control block. This is a data structure that stores critical information about a process, such as its ID, state, priority, CPU registers, and allocated resources. For example, the PCB is like a dossier that contains all the details about a process, allowing the OS to manage it effectively. Okay, last we have context switching. Now, context switching is the process of saving the state of one process and loading the state of another. This allows the CPU to switch between tasks efficiently. Then it ensures multitasking by enabling multiple processes to share the CPU. However, it can also introduce overhead. For example, when you switch between a Word document and a web browser, the OS performs a context switch to manage the transition seamlessly. So, for example, can you think of scenarios where multitasking supported by context switching improves your productivity? We can say that we can have like editing a document while a video conference runs in the background. This could be an example for that. Okay, now we'll see process scheduling. Now we have three main types of like scheduling types. First is long-term scheduling, which determines which processes are admitted into the system for processing. This ensures the system is not overloaded with too many processes. Then we have short-term scheduling, which decides which process in the ready queue gets the CPU next. This happens frequently to maintain multitasking. Then third is medium-term scheduling. It like temporarily removes processes from memory to optimize resource use, also known as swapping. So we can think of like long-term scheduling as selecting guests to invite to a party, short-term scheduling as deciding who gets served next, and medium-term scheduling as asking a guest to step outside for a moment to make space for others. So this could be an example if you want to think like that, how the PC is working. Okay, now CPU scheduling algorithms. Well, to manage CPU scheduling effectively, the OS uses various algorithms, each suited for different scenarios. First is first come first serve, FCFS, which is basically a queue, like queue has first come first serve option. So processes are executed in the order they arrive, like a queue at a store. So if you're familiar with queue, then you'll know if you are like standing waiting in a queue at a store, whoever comes first will go first. So the processes are executed in this order. It is basically simple and fair for all, but it can lead to longer wait times for processes arriving later. Okay, next is shortest job next, SJN. The process with the shortest execution time is executed next, minimizing average wait time. So the process that with the shortest execution time is executed next. This is how it works. It is efficient for batch systems, but it may cause starvation for longer processes. Last, we have round robin. Like processes are executed in time slices like quantums, ensuring fairness by allowing each process to run for a fixed time. It is ideal for time sharing system, but performance depends on the time quantum size. For a practical example, we can say, imagine a printer queue. The first come first serve algorithm prints documents in the order they were sent. However, if one document is very large, SJN could prioritize smaller documents to clear the queue faster, and round robin could ensure everyone gets their documents printed without waiting too long. So this is how we can see how the PC works with these all three algorithms. Okay, so in modern computing, achieving efficiency often involves concurrency, where multiple tasks are performed simultaneously. To understand this concurrency better, let's compare processes and threads. Now, first we have process, where basically a process is an independent execution unit with its own memory space and resources. For example, opening two browser windows creates two separate processes, where thread is a smaller execution unit within a process, sharing the process memory and resources. For example, like opening multiple tabs in the same browser window creates threads. Second, for resource sharing, like processes do not share resources directly with other processes, ensuring better isolation, but threads share memory and resources with other threads in the same process, enabling faster communication and lower overhead. Third is execution overhead. Processes require higher overhead because they involve context switching, which saves and restores the state of the process, where threads have lower overhead since they share memory and require minimal context switching. Fourth is communication. Processes require inter-process communication. IPC mechanisms like pipes or sockets, which can be slower, where for threads it's easier communication as threads within a process share the same memory. Okay, next is failure impact. Failure of one process doesn't impact others, providing better stability, where failure of a thread can affect the entire process since all threads share the same memory. So if we say, think about a real world analogy, imagine processes as separate houses with their own utilities, while threads are like roommates sharing the same house. So communication is easier among roommates like threads, but if something goes wrong in one room, it might affect the entire house. So Basically, processes offer better isolation, making them more stable but resource intensive. Threads, on the other hand, are lightweight and efficient but come with the risk of affecting the entire process if one threads fail. Okay, so um, now we'll see the user level versus kernel level threads. Threads can be implemented at two levels, user level and kernel level. Each has unique characteristics and trade offs that make them suitable for different applications. First is definition. If we say user level threads, like they are managed entirely in user space by the application without kernel involvement. For example, if you think about Java green threads used in early version of Java operate in this way, where kernel level threads are managed directly by the operating system kernel, enabling deeper integration with system level resources. For example, POSIX threads or pthreads are a common implementation. Next is switching overhead. So user level threads have low switching overhead since the kernel is not involved, and this makes context switching between threads faster, where kernel level threads have higher overhead because switching requires interaction with the kernel, and this involves saving and restoring kernel level data structures. Third is performance. So user level threads are faster because kernel interaction is minimal, making them ideal for applications with lightweight threading need, where kernel level threads are slower due to the involvement of the kernel in managing threads, but they provide better system level resource control. Okay, fourth is portability. User level threads are highly portable as they are independent of the operating system. But kernel level threads are depend on operating system support, which can vary across platforms. So for the examples, we can say that Java green threads are an example of user level threads, providing lightweight threading within the Java virtual machine. And POSIX threads like pthreads, on the other hand, exemplify kernel level threads integrating tightly with the operating system. So if we like to say a comparison analogy, we can say think of user level threads as carpooling within your neighborhood, quick and independent of traffic signals, where kernel level threads are like buses controlled by city traffic systems, which is slower but capable of handling larger scale coordination. So we can say that user level threads excel in lightweight tasks where portability and speed are key, while kernel level threads shine in applications requiring robust system level resource management. Okay, so here we'll see deadlock versus starvation. Well, concurrency in operating systems can lead to issues like deadlock and starvation. These terms describe situations where processes are unable to make progress due to resource conflicts, but their causes and impacts differ. First of all, deadlock, which occurs when processes wait indefinitely for resources, preventing any of them from making process or progress. For example, imagine two cars blocking each other at a narrow bridge with neither able to move forward. And starvation happens when a process waits indefinitely because resources are unfairly allocated to others. For example, a car waiting in a queue while other cars keep cutting in front. Second is cause. So, what caused these issues? Deadlocks are caused by circular dependencies where each process holds a resource the other needs. For example, if you say process A holds resource 1 and needs resource 2, while process B holds resource 2 and needs resource 1. So that could be a deadlock situation. For the starvation, it occurs due to biased or unfair scheduling, where lower priority processes are repeatedly overlooked. For example, a low priority print job never gets executed because higher priority tasks dominate. So, what is the impact of these two type of problems? For deadlock, all processes involved in the deadlock are affected and the system comes to a standstill. But on the starving process, only the starving process is affected while other processes continue to execute. Last is resolution. So resolving deadlocks requires prevention or recovery mechanisms such as deadlock avoidance, like ensuring resource allocation doesn't lead to circular dependencies. For example, like bankers and detecting a deadlock and terminating or restarting processes. These are recovery mechanisms we can use to resolve deadlocks. And for starvation, it is resolved through improved scheduling algorithms like priority aging, like gradually increasing the priority of waiting processes. So for a real life scenario, we can say think of deadlock as a complete traffic jam at an intersection, while starvation is like a single car stuck at a stop sign because other cars keep passing by. So we can say deadlock halts the entire system, requiring immediate intervention, whereas starvation affects only specific processes, but it can degrade system performance over time. Memory management is a critical function of an operating system, and understanding the differences between primary and secondary memory helps clarify how data is stored and accessed in a computer system. So first, if we look at the speed, primary memory such as RAM and cache is extremely fast. It provides the speed required for a computer to process data in real time. For example, when you run an application, its data is loaded into RAM for quick access. While secondary memory like hard drives or SSDs is relatively slower but sufficient for storing large volumes of data. For example, files on your hard drive are loaded into RAM when you open them. Otherwise, it stays there. Second is volatility. Primary memory is volatile, meaning data is lost when the computer is powered off. It doesn't store anything. So unsaved work in an application is lost if the computer shuts down unexpectedly. Where secondary memory is non-volatile, so data persists even when the power is off, and documents saved on your SSD remain accessible after rebooting your computer. Third is size. So primary memory is typically smaller in size, measured in gigabyte. For example, a typical computer might have 16 GB of RAM, where secondary memory is much larger, ranging from gigabytes to terabytes. Hard drives can store 1 terabyte or more of data. Okay, next is cost. Primary memory is more expensive per gigabyte due to its high speed and advanced technology, where secondary memory is cheaper per gigabyte, making it suitable for long-term data storage. Well, if we look at the examples for primary memory include RAM and cache memory, which are used for immediate and frequently accessed data, where secondary memory examples include hard disk drives, solid state drives, and optical disks like DVDs. So, at the end, if you think of a real world analogy, think of primary memory as your desk where you work. It's fast and keeps everything you are currently using. And secondary memory is like a filing cabinet, slower to access but great for storing things long term. So, to conclude that, we can say primary memory enables fast, real-time processing but is limited in size and volatile. And secondary memory is slower but non-volatile, larger and cost-effective for storing vast amounts of data. Okay, so here memory allocation is a fundamental aspect of operating systems. It determines how processes are assigned memory in a system, either in a contiguous or non-contiguous manner. Now let's explore the differences between these two approaches. First is the definition. So contiguous allocation is like it allocates memory in one continuous block for a process. This approach requires processes to occupy consecutive memory locations. For example, imagine booking an entire row of seats at a theater. The seats must be adjacent. For non-contiguous allocation, it allocates memory in scattered blocks, allowing processes to occupy non-adjacent memory spaces. For example, this is like booking seats scattered across a theater, wherever space is available. Second is flexibility. Now, contiguous allocation is less flexible as it requires sufficient consecutive memory to be available. This can lead to memory not being utilized efficiently if large blocks aren't available. Then non-contiguous allocation are more flexible because it allows memory to be allocated in smaller scattered chunks. This approach is better suited for systems with fragmented memory. Now, speed. So, contiguous allocation is faster because memory is accessed sequentially, minimizing overhead. And for example, data stored in continuous locations can be read quickly in bulk. Non-contiguous allocation is slower due to the need to access scattered memory locations, which may involve additional lookups. Like if you say retrieving scattered memory blocks requires more effort, like searching for files in multiple folders. Next is fragmentation. So contiguous allocation suffers from external fragmentation, where small unused memory gaps exist between allocated blocks. For example, if memory is split into smaller segments, larger processes may not fit even if there's enough total space. Where Non-contiguous allocation does not suffer from external fragmentation, as processes can use memory in scattered blocks. For example, paging and segmentation eliminate this issue by breaking processes into smaller chunks. Okay, now for the example, we can say contiguous allocation is used for simpler systems or single partition processes where simplicity and speed are prioritized, where non-contiguous allocation used in advanced techniques like paging and segmentation to optimize memory utilization. Now, if you want to look at a real world scenario, think of contiguous allocation as parking in a single long space for your vehicle, while non-contiguous allocation is like parking in multiple smaller spots spread across a lot. So basically we can say that contiguous allocation is faster and simpler but inflexible, while non-contiguous allocation offers better memory utilization and flexibility at the cost of additional complexity. Okay, now when a process runs, it interacts with memory using two types of addresses. First is logical and then physical. Now, understanding the difference is crucial to grasp how memory management works in operating systems. Well, let's get started with the definition. So, the logical address is generated by the CPU during program execution. For example, when your program accesses a variable, it uses a logical address. Next is physical address. So the physical address refers to the actual location in the memory hardware. For example, this is where the variable resides in RAM after being mapped by the operating system. Now we have visibility. Logical address is not visible to the user as it's an abstraction created by the CPU. Like for example, the operating system uses logical addresses to simplify memory management. Now, on the other hand, physical addresses are visible and managed by the operating system for direct interaction with hardware. For example, the operating system uses the physical address to fetch or store data in memory. Okay, now third is mapping. So, logical address mapped to a physical address by the memory management unit, MMU, a hardware component. For example, this mapping allows processes to use memory independently without interfering with each other. Physical address directly used by the memory unit for read-write operations after mapping. And the mapped physical address is where the data is stored in RAM. Okay. Then logical address represents a virtual address used during program execution. If you say the OS translates logical addresses into physical ones seamlessly, where the actual address in the RAM where data resides is the physical address. So, for example, when data is read from or written to memory, the physical address is accessed. Fifth is usage. So, logical address is used in programs to reference memory locations abstractly. For example, like code written in high-level languages uses logical addresses. For physical address, it is used in hardware to perform memory operations. For example, like memory controllers and devices access physical addresses directly. Well, now if you want to look at a real world scenario, think of the logical address as the street address of a building, while the physical address is the actual apartment number where you live. The postal system, like the MMU, maps the street address to your apartment. So, to conclude this, we can say that logical addresses simplify programming and ensure isolation between processes, while physical addresses represent the real locations in RAM. The MMU bridges the gap between these two types of addresses to enable smooth memory management. Okay, now we'll see paging and segmentation. So, paging and segmentation are two memory management techniques designed to optimize the allocation of memory and minimize fragmentation. Now, let's see how they work and their advantages and disadvantages. So, here we'll start with the definition and purpose. Like paging divides the physical memory into fixed size blocks called pages. Each process is assigned memory in these pages, which may be scattered throughout physical memory. For example, think of paging as dividing a book into numbered pages for easier access. Well, the purpose of paging is like to help avoid external fragmentation and optimize memory utilization. Okay, for segmentation, we can say it divides memory into variable sized blocks, each representing a logical segment like code, data, or stack. This is like separating chapters in a book, each with a logical purpose. Now, let's see the advantages of paging. So, paging eliminates external fragmentation because processes don't require contiguous memory. It simplifies memory management by standardizing block sizes. But paging introduces overhead because of the page table used for mapping logical or to physical addresses. It can cause internal fragmentation if processes don't fully utilize allocated pages. So, these are the advantages and disadvantages for paging. Now, see the advantages of segmentation. So, segmentation aligns with how programs are logically structured, making it easier to handle code, data, and stack separately. It allows flexible memory allocation for each segment. So, these are the advantages, but there are some disadvantages also. Like segmentation is vulnerable to external fragmentation, and the management of variable size segments can be complex. But if we say like if you like to know more, and if you like to see some examples of paging systems, we can say that like paging is used in most modern operating systems including Windows, Linux, Unix. So how we can use paging in Windows? Well, it implements virtual memory using paging for efficient memory allocation, where in Linux, which uses paging for process memory management. and in Unix, it combines paging with segmentation for enhanced flexibility. So imagine paging as storing data in uniform boxes of the same size, while segmentation is like storing items in custom sized containers depending on their shape and size. Okay, now we'll see virtual memory. Now, virtual memory is a fundamental concept in modern operating systems that allows us to run large programs or multiple applications efficiently by extending the computer's memory capacity beyond the physical RAM. Now, what is virtual memory? Basically, virtual memory is a memory management technique that uses a combination of physical memory RAM and disk space to provide the illusion of a larger memory space to processes. For example, think of it as borrowing disk space temporarily when your RAM is full. Now, there are some benefits also. So, first of all, virtual memory ensures that only the necessary portions of a program are loaded into RAM, optimizing memory usage. And then it enables processes to use more memory than physically available in the system. Then each process gets its own isolated memory space, ensuring security and preventing interference. Now, what are the techniques used in virtual memory? First, we can use paging, which divides memory into fixed size blocks and maps them between logical and physical memory. Because if you say like only the currently needed pages of a program are loaded into RAM while the rest remain on disk. So this is how we can use paging to make it a virtual memory. Then demand paging. Demand paging is like pages are loaded into RAM only when they are accessed, reducing unnecessary memory usage. So, for example, think of it as streaming a video. You only load what you need as you watch. Then trashing. Trashing is like when you excessively paging reduces system performance as the OS spends more time swapping pages than executing processes. So, for example, if your computer becomes slow while running many applications, it may be experiencing trashing. So, if you want to look at a real world scenario, imagine virtual memory as having a notepad RAM for active tasks and a filing cabinet disk for less urgent tasks. When the notepad is full, you temporarily store some notes in the filing cabinet and retrieve them as needed. Okay, so now we'll look at file management. We'll just go with the overview because we have we'll learn more detail in our next coming up slides like lectures throughout the course. So for the first lecture, we'll just go through the overview. Well, file management is a critical function of an operating system. It ensures that data is organized, stored and accessed efficiently by both users and applications. So, the file system organizes and stores files in a hierarchical structure such as directories and subdirectories. This structure makes data management very easy and efficient. So think of your computer's file system as a digital filing cabinet where folders act as drawers and files are the documents inside them. So the hierarchical design simplifies navigation, retrieval, and storage of files. Now, what are the operations we can do on files? So we can create, read, write, delete. These are four operations we can do. So files can be created to store data or applications. Reading retrieves the content of a file. Then you can write or modify content on a file, or if you want, you can delete a file. So when you will delete or remove a file, when you're no longer needed, on some operating system it go to trash or recycling bin. So then we have file access methods, like how can you access the files. So we have three methods. First is sequential access, like processes files in a specific order, like reading a book from start to finish. We can then like playing a video file from the beginning. So this is how we can like sequentially we can access the file. Then there is a direct access option, like it retrieves specific data quickly without processing the entire file. So accessing a particular record in a database, whatever you need. Then third is indexed access, means it uses an index for faster lookups, like a table of content in a book. So file management ensures that data is stored in a structured way and provides various methods for accessing and manipulating files based on user needs. It's an essential part of how operating systems maintain efficiency and usability. Okay, now directory structure. After the file management system, we'll go through the directory system. Like directory structure of an operating system determines how files are organized, stored, and accessed. So there are three levels of directory. Like a single level directory is a flat structure where all files are stored in a single namespace. Then two level directory, where a two level directory structure provides each user with their own directory, creating separate namespaces for their files. Then third is a hierarchical directory, which allows multiple levels of directories and subdirectories, providing better organization and scalability. Now, file allocation methods determine how files are stored on disk. Choosing the right method impacts file retrieval speed, memory efficiency, and system performance. So first is contiguous allocation. In contiguous allocation, files are stored in consecutive memory blocks. This ensures fast access since the blocks are stored together. Now, if you think of a book with all its pages bound in order, it's quick to read sequentially. Now, second is linked allocation. So files are stored as a linked chain of blocks scattered across the disk, with each block pointing to the next. So if you imagine a treasure hunt where each clue leads you to the next location, this is how it's allocated. Third is indexed allocation. Like it uses an index block that holds pointers to all the file blocks, allowing direct access to any block. Like this is like having a table of contents in a book that points you directly to specific pages. Okay, next is device management basics. So device management is a crucial aspect of operating systems, ensuring that all hardware components are work together seamlessly. So let's see how so let's start with the definition. Well, it is a process of controlling and coordinating the use of hardware devices by the operating system. So it ensures that devices operate efficiently and without conflicts. Well, if you think of a for example, when you plug in a USB device, the OS detects it, installs the necessary drivers, and makes it ready for use. Now we have IO devices. So this includes devices like keyboards, like input devices includes keyboards, mice, and scanners that send data to the computer. um, like typing on a keyboard sends text to a word processor. And as an output device, this includes like devices, monitors, speakers, and printers that display or play data from the computer. Like your monitor displays the slides you're working on, like that. And now we also have some storage devices like SSDs, hard drives, and USB drives for storing and retrieving data, like saving a file on your hard drive. These are the types of devices that managed by device management drivers. Now device drivers and their role. Uh, like these drivers are software components that enable the operating system to communicate with hardware devices. Like a printer driver translates print commands from the OS to a language the printer understands. So it is like the medium between them. Well, without drivers, the OS cannot utilize hardware devices effectively, because when you update your graphics card driver, it improves performance and compatibility. So it is very important, and it ensures efficient operation and coordination of all hardware devices through input, output, and storage management. And with the help of drivers, the OS provides seamless interaction between hardware and software. Okay, so now we'll look at IO management, like input output. So IO management handles the interaction between the CPU and input output devices. It ensures the data is transferred efficiently between hardware components. So we'll see first the interrupt handling. Now, interrupt handling is a mechanism where the CPU temporarily stops its current task to address an external event or signal. For example, when you press a key on the keyboard, an interrupt is triggered to notify the CPU of your input. So this ensures the CPU can respond promptly to critical events without continuously polling devices, saving resources. Second is buffering. So buffering involves temporarily storing data in memory while it's being transferred between devices that operate at different speeds. Like for example, when you stream a video, a buffer stores a portion of the video to prevent playback interruptions caused by network speed variations. Next is spooling. So spooling means if we say simultaneous peripheral operations online. So spooling queues and stores data temporarily for devices that process data sequentially. For example, when you send multiple documents to printers, spooling queues them in order and sends them to the printer one by one. So these IO management mechanisms like interrupt handling, buffering, and spooling ensure efficient data transfer and device coordination, enabling smooth operation of input-output processes in a system. Okay, now we'll look at the introduction to networking in operating system, which is very important topic. So like networking plays a vital role in modern computing by enabling resource sharing, communication, and data exchange between devices. The operating system acts as the backbone of these network functionalities. So why networking? Because networking enables multiple devices to connect and share resources such as files, printers, and internet connections. For example, think about a company where employees share a single printer or access shared files on a server. This is possible because of networking. So, networking facilitates communications between users, systems, and applications across local and global distances efficiently. So, the OS manages network connections by detecting and configuring hardware like network adapters and maintaining reliable communication between devices. So first we can have like connection management, which by establishing and maintaining connections between devices on a network. Then data transfer reliability, like ensuring data packets are delivered accurately and efficiently. Then security protocols, like implementing protocols like encryption to safeguard data during transmission. So for example, like when you connect to Wi-Fi, the OS negotiates network settings, manages your connection, and ensures secure connection communication. Now, some network protocols which are very common, we can say TCP/IP, HTTP, and FTP. So TCP/IP enables reliable data transmission between devices over the internet, and HTTP handles web communication and data exchange between web browsers and servers, where FTP facilitates file transfer between devices. So we can say that networking is very essential for modern computing, and the operating system plays a critical role in managing connections, data transfers, and security. Like common protocols like TCP/IP, HTTP, and FTP ensure smooth and reliable communication between devices. Well, distributed operating systems are a key innovation in modern computing. They manage multiple computers as a single system, enabling efficient resource sharing and parallel processing. Now, a distributed operating system manages a group of networked computers to appear as a unified system to the user. So it can share resources and can do parallel processing, or it can has processing. So the examples are like Hadoop, Kubernetes. So Hadoop is used for managing big data processing across distributed clusters. Like companies like Facebook and Amazon use Hadoop for large scale data analytics, where Kubernetes orchestrates containerized applications across multiple servers, ensuring reliability and scalability. It is widely used in cloud computing to manage workloads across data centers. So these are some benefits also. They have some benefits like distributed systems can grow by adding more like machines to handle increasing workloads. So it's more scalable. So and it's also fault tolerance. It has fault tolerance, like if one machine fails, the system continues to operate using the remaining machines. Then it can do parallel processing, which allows faster computation and reduced response times. There are some challenges also, like complexity. These are like managing and coordinating multiple machines requires sophisticated softwares, and it is dependent on network. So it's very important to have a reliable network. So it relies on heavily on network performance and stability. Then like there is a security risk because data is distributed across machines can be more vulnerable to attacks. So we can say it's a very powerful, scalable and fault tolerant computing by managing multiple machines as a cohesive system, and they are essential for handling modern challenges in big data and cloud computing. So next is system security and protection. So these are like critical functions of an operating system, ensuring the data and resources are safeguarded against unauthorized access and potential threats. So authentication is the verification of the identity of a user or system to ensure secure access. Like what you all do, like you have a user profile or you have to put a password and username to log into your system. It is just the authentication. And also you have administrator in Windows, and then under the administrator you can have multiple users, and you can like share any rights with them. So this is how it works. Then authorization, like authorization determines the access rights and permissions granted by administrator to authenticated users, as I just said. So authentication acts as the first line of defense against unauthorized access. And then a manager might have access to sensitive files and company system, while a regular employee can only access basic resources. Where once a user is authenticated, the OS checks their permissions to determine which resources they can access. So first step is admin and then the user. So admin has all the rights, authentication, and then admin can add any user and authorize any user any right. Next is encryption and firewall. So encryption secures data by converting it into unreadable formats, which can only be decrypted by authorized user. And it also monitor and control network traffic to prevent unauthorized access. So a firewall can block malicious traffic trying to access your computer from the internet. Okay, now we'll see some popular operating systems like Windows OS. We all know Windows is known for its user-friendly interface and broad compatibility with software, making it a favorite in both personal and enterprise environment. And Microsoft Office is a key productivity suite in Windows. Then Linux OS. Linux is very popular because it's open source. You don't have to buy Linux. You can have Linux. It's open source. It offers flexibility, security, and a robust development environment. It's basically more useful for developers. So most of the developers use Linux system because it's open source and there's a lot of flexibility. And we have a lot of popular distribution like Ubuntu, Fedora, and Debian. These are some of the most popular Linux distributions, and it's often used in servers like programming and cybersecurity due to its stability and customizability. Then Mac OS from Apple MacBook. So Mac OS is designed specifically for Apple hardware, offering a seamless and easy user experience. So it integrates well with other Apple devices like iPhones and iPads, providing advanced media capabilities and polished user interface. So Apple also have some other built-in softwares, and it's also very useful and easy access. It's very fast. So Mac OS is very fast. So next we can say mobile OS, like Android versus iOS. Like every mobile phone has an operating system like a computer. So nowadays we have like Android or iOS. Like Android offers customizable a wide variety of devices are compatible, like Samsung, Google Pixel, OnePlus devices. These are these uses Android operating system, where iOS is only for Apple, and the App Store offers exclusive apps and seamless integration with Apple products like AirPods and Apple Watch. And you can find all like lot of softwares in Apple Store. Now we'll see the IoT devices for operating system for IoT devices. So IoT means the Internet of Things, which connects billions of devices worldwide, from smart thermostats to industrial machines. Operating system plays a crucial role in managing these devices. So there are some challenges also, like resource constraints, because IT devices often have limited processing power, memory, and energy resources, which makes OS design critical. So, like for example, a smart sensor might only have a few kilobyte of memory. So there are some security vulnerabilities also, like IoT devices are often targeted by hackers due to weak security protocols. So unsecured smart cameras can be exploited for unauthorized surveillance. So like managing millions of connected devices requires robust systems that can handle diverse hardware and networks. So we can have tiny OS and RIoT, Contiki. These are the types of OS for IoT devices. So Tiny OS is a flexible open source OS designed for wireless sensor networks. And then RIoT, which is an energy efficient OS supporting multiple IoT devices and protocols with a strong focus on modularity. Then Contiki, which is designed for low power wireless IoT devices, enabling communication over IPv6. Now, if you want to know about some real world applications, like you can say smart homes, like IoT operating systems power devices like smart thermostats, lights, and security cameras or security systems. Then industrial automation, like in factories, IoT systems manage sensors and actuators for real-time production monitoring. On healthcare devices, like wearable devices like fitness trackers and medical monitors rely on IoT operating systems. So these are some real life scenarios or examples or applications for IoT devices. Now, future trends in operating systems. So first we have AI integration, then edge computing, and enhanced security measures. So operating systems are constantly evolving to meet the demands of modern computing. So artificial intelligence is becoming a critical component of operating systems to optimize resource management and enhance user experience. So like AI driven operating systems can predict resource needs and allocate CPU memory and storage dynamically. So voice assistants like Siri and Cortana rely on AI integrated into the OS to process user queries and provide responses. Well, then we have edge computing, which allows data processing at the network's edge, closer to the resource of data, rather than relying entirely on centralized servers. So, for example, smart cameras process video footage locally, reducing the need to send all data to the cloud. Then we have enhanced security measures. So, with the rise of cyber threats, operating systems are incorporating advanced security features to protect users and systems. So, These are the features like encryption, authentication, anomaly detection. um, so encryption ensures data is secure during transmission and storage. Authentication or multi-factor authentication strengthens identity verification. Then anomaly detection, like AI powered systems detect unusual activity, like preventing breaches. These are the steps. So, to conclude this, we can say the future of operating systems is driven by AI integration, edge computing, and advanced security measures. These trends ensure systems are faster, smarter, and more secure, and it's meeting the needs of an increasingly connected world. So that's all for today's lecture. Um, let me know if you have any question about this lecture. You can post any question on the discussion forum, or you can email me anything, and then you will get the next recorded lecture link on the next on the content page, next week's content page. um, so in each week's content information or page, you will get all the information for that week. So that's all for today. Thank you.